Here is a sequence. It's taken from the textbook, exercise 2.1.3, number little Roman 5. It's on page 27. Our conclusion is an atomic sentence S. We have three premises. The first premise is a conjunction, both R and P. The second premise is a conditional. If R, then either S or Q. And then the third premise is a negation. It's a negation of a conjunction. And our conclusion then is the atomic sentence S. And if we ask, well, what will be the annotation over here? How will we prove S? When we look at the premises, we find S here in the consequent place. It's the left disjunct of a disjunction that is the consequent of a conditional. And we can prove the consequent of a conditional if we have its antecedent. And we do have its antecedent on line 1. So we can take out R using ampersand elimination. Then we can do the arrow elimination from the conditional on 2 and its antecedent on 4. We prove its consequent, either S or Q. So the assumption set is 1 and 2, because 2 rests on itself and 4 rests on 1. But now, to prove S, our conclusion, we need not Q, the denial of the right disjunct. And then we can get not S by wedge elimination, right? From 5 and a line number on which we prove not Q. So we know we can get S from 5 by wedge elimination if we can get not Q. But clearly, not Q is not itself up here. We've got Q here, and we've got Q here as the left conjunct of a conjunction that is negated. So clearly we can't get not Q by any elimination rule, and nor is there an introduction rule for the negation sign. So we're going to have to use reductio. And what that means is that we assume the denial of what we want to prove. So we assume Q, an assumption for reductio. Now we need two sentences to us. We need two sentences, one of which are denials of each other. So one of them at least has to be a negation. So when we go looking, we see that we already have a negation on line 3. It says, it is not the case that both Q and P. So if we could prove both Q and P, so to speak, we could prove this, then we'd have two sentences that deny each other. And both Q and P is a conjunction. We have its left conjunct here on 6. We can get its right conjunct from 1. So that's 1 ampersand elimination. And now we put the two together. Q and P. 6, 7 ampersand introduction. And now we do have our two sentences. So here we say there's a sentence on line 3 and there's a sentence on line 8, and they can't both be true. So if the sentence on 3 is true, and the sentence on 8 were true, 1, 3, and 6 would, they can't all be true, 1, 3, and 6, because if 3 is true, then this is true, and if 1 and 6 is true, then this is true, but both Q and P, and it's not the case that both Q and P can't both be true. So we must reject one of these three assumptions, 1, 3, or 6. So we reject 6, we deny 6. Instead of saying Q, we say not Q. The assumption set here is the union of the assumption sets of 3 and 8, but minus the reductio assumption. So we get 1, 3 here. 6, the assumption on 6, is discharged by being denied. Here we assumed Q. That led to a contradiction, because the sentence on 8 and the sentence on 3 cannot both be true. And so we deny the assumption that leads to the contradiction, and that gives us not Q. And then 5, 9, wedge elimination, gives us S. And so this is a proof that uses ampersand elimination and arrow elimination and reductio and ampersand introduction and wedge elimination.